Hello everyone, welcome to the video session of push down automata. In this session I am going to discuss in detail about what is push down automata and how is the various functionality there for push down automata. And as it defined that a push down automata is an automata similar to the automata of DFA. We have discussed about NFA or DFA. So this is an automata which is defined for context free grammars. So we'll see in detail what is this push down automata is all about. So in this slide it shows that what is the automata model for a push down automata. So we can see that very well that there is a finite control state, okay, which is you can also call a finite automata, okay, which is consists of number of state with a starting state and may or may not be some acceptance state. And input type indicates the input stream. The additional component to this push down automata is a star. So the component which push down automata has, and additionally compared to our deterministic finite automata or non-deterministic finite automata, is a star, where always we will have a pointer which is pointing to the topmost symbol of the star. So the finite control or the PDA can read the symbol which is present on the top of the star. So these are the operations that a PDA or push down automata can perform, okay, on the star. Okay. So first of all, it can push any symbol onto the star. Okay. It can pop them later. Okay. So all it will be depend upon how and what is the situation, what is the transition to be done at any state of time. Okay, and this stack can grow or shrink. Okay, there is no limit in the size of the stack, but at any moment of time, the size of the stack is going to be finite. So this is the working model for PDA, means how a PDA works when given some input. Okay, so let us see. It has a finite state control which will read the input one symbol at a time, very similar to the finite automata which we have already discussed. And along with this operation, PDA observes a symbol on the top of the stack. So that's why any transition in PDA depends on or based on the current state where the PDA is, then the input symbol and the topmost stack symbol. So based on these three information, a transition is in PDA is defined. Okay. In addition, a transition can also happen spontaneously from any state to another state. That means we can say that PDA can make transition on E string, or I can say empty string, or E moves. Okay. So typically transition looks something like this, which is shown in this diagram. Let's say from state Q1 to Q2, okay, a transition is defined. So it is defined in with two information, A, comma, B to C. So here it indicates the first part indicates its input symbol, which input symbol is the next symbol to be seen. So from Q1 on, if an input symbol A is observed, then it says that, and the symbol that is to be popped from the stack is B, and the symbol that is to be pushed into the stack is C. Right. So in this way, a transition is defined for PDA model. So let us discuss the transition in detail. That it consumes a symbol from the for transition from the input, and it changes the state from one state to another, or as you say that it may stay in the same state. And one more step is that it replaces the symbol at the top of the stack by any string. Okay, so this any string can be no string, or sometimes only one symbol is replaced by another symbol, or there may be one symbol, it may replace by more than one symbol. So let us see some cases which will indicate what are the different kind of replacement that is done during the transition in PDA. So replace with no symbol. This is an example of replace with no symbol. So the transition is indicated something like this: a comma lambda, okay, 2 lambda. So it indicates that the lambda is going to be popped and lambda is going to be pushed again. So it is indirectly saying that no change. Okay, there is no change in the stack. So left hand side is the status of the stack before, left hand side of this arrow, the status of the stack before the transition and after the transition. So here there is no change. So it may happen that no symbol is replaced in the stack. Second operation, the top of the stack is replaced by another symbol. Whatever the current symbol is present on the top of the stack, it can be replaced by another symbol. So you can see here currently the B is the symbol which is present on the top of the stack. Input symbol is A. So on the transition on input symbol A, and when B is on the top of the stack, okay, so this B will be replaced with the symbol C on the top of the stack. So on this transition, the next symbol which is going to be on the top of the stack is C, as indicated on the second stack. Next is it can be replaced with more than one symbol. One symbol can be replaced by more than one symbol. So it is an example, and we'll see more examples while discussing the detail about this PDA. Okay. So any one symbol which is popped from the stack and it is replaced by and we'll make a push of more than one symbol. So this case is indicated here. Next, let us discuss what are different type of PDA happen. So mostly we'll discuss about non-deterministic PDA. Okay. So PDA may be deterministic or non-deterministic, and as we know that non-deterministic is more powerful. Okay. So by non-deterministic we can see that many grammars, many context-free grammars, we can define the PDA. Okay. So it is also we should be noted that PDA recognizes all and only the context-free language. If a language is context-free, then we can define or we can design a PDA for it. So this is the formal definition for PDA. So a push-down automata or PDA is described by 7 tuple. Okay. So some symbols are familiar, which is already been defined for NFA or DFA. So that is Q, sigma, and delta, the transition function, starting symbol, and final state. So the additional symbol which are introduced in PDA are a tau, which defines the finite stack alphabet. So what are the symbol to be used in or that can be used in the stack. Next, a Z0 or Z0 is a starting symbol of the stack, which indicate what will be the starting symbol in the stack. Okay, so stack must start. So stack, when the stack is empty, it must start with a starting symbol. So this, to avoid the confusion, this G0 is used. So G0 is the starting symbol of the stack, and the transition function is here is a different. So it is the domain is here the Cartesian product of the Q and sigma E and tau E, where the sigma E indicates all the alphabet set including E. Since we are defining a non-deterministic case, so here the transition is also allowed on E, on the E symbol or an E move. Okay. Similarly, the tau, the symbol tau in E indicates all the symbol including E. So that means the stack can contain empty string. So any transition, okay, we'll define the transition later, but just for information that any transition will be done from a state, okay, from a state by taking the input symbol and looking at the topmost symbol of the stack. Okay, it will lead to another state with a different status or maybe same status on the stack. Okay, so that's why the domain is Q cross sigma E and tau E, and the domain in the range is your power set of the Cartesian product of your Q and tau E. Alright, so we'll see some more examples on this transitions, and it will be more clear. So let us discuss one example of NPDA for the palindrome language, which we already know the palindrome language, that is a language which having a string, so that the reverse of the string is same as the original string. Okay, so let us denote the language in this way, that is L equal to WWR, okay, such that W is in 0, 1, it's in the 0 more occurrence of 0 and 1s, and WR indicates the reverse string of W. Okay, so how can we develop a non-deterministic PDA for this one? So let us assume a state, the starting state is Q0, and also we assume that Q0 can make guesses. Okay, assume that in Q0 you will stay, the transition or the control will stay in Q0 till it has not yet seen the end of the string W. So once it has seen W, it will go to the state Q1. Okay, and then it will try to see WR and match with the W which is already been pushed into the stack. Okay, and by looking at every symbol, okay, the popping of the symbol, we find that the current input symbol, okay, the consumed input symbol is same as the current input symbol, same as the symbol which is on the top of the stack. Then it consumes the input symbol and pop up the stack. Then proceed to the next case. If there is no match, definitely this branch dies. Okay, then definitely, and we are using an NPDA, so definitely for a non-deterministic case, we'll have another branch to proceed. Alright, so like in this manner, it will proceed. Okay, and you will check that if the stack is empty, okay, then we infer that we have indeed seen the WR. Okay, because we will only pop up the stack when we see a symbol, input symbol is on the top of the stack. Alright, so in this case it accepts the input, okay, that has been read till this point. Okay, whatever it is been seen this point till the stack is empty. Okay, it assumes that is an accepted string. Okay, so this is defined by the state Q2, so we can make a transition to Q2. So let us overall define how the transition of this non-deterministic PDA. So here is the transition function for the PDA of the Palindrome language. Let us analyze the transition function of this PDA. Okay, so the first two transitions shows that, okay, being at starting state Q0, okay, on the input symbol 0 and 1, and having the Z0, the starting symbol of the stack on the top of the stack, okay, what transition is going to be made? Okay, so on looking at the starting state Q0, okay, and doesn't matter whatever the symbol is, 0 or 1, if we found that Z0 is on the top of the stack, okay, so the next state is going to be that we will stay in Q0 by pushing the current input symbol into the stack. That is indicated by this pair, that is Q0 0Z, similarly Q0 1Z. Now second case is that being in state Q0, if we see, or if you see the current input symbol as 0, okay, so it doesn't matter whether there is a 0 or there is a 1 on the top of the stack, we are going to push this. So next state indicate that we will stay in the state Q0 and we're going to push this symbol into the stack. That can be indicated right here. Okay, same is applied for the symbol 1. Okay, so this is the case which indicate that we have not yet seen W. So these are the part of W. So this all indicate that these symbols that have been consumed or that have been seen in the input string are part of W. The W has not, end of the W has not yet been arrived. Now based on the case when the automata finds that it has arrived at the end of the W, it is going to make a transition, and that is indicated that then transition is spontaneous. That transition is spontaneous, it means to say that will be made on the input symbol E with the empty string. So that is indicated by these three transitions. So being at Q0 on input symbol E, doesn't matter what symbol that is present on the top of the stack, the state is going to change from Q0 to Q1, okay, keeping the stack unchanged. Okay, and next in Q0, so in Q1, in the state Q1, okay, you can see that if depend upon the input symbol, whatever the input symbol, it is matched with the topmost symbol that is present on the stack. Now let us see this case. If on the state Q1 the input symbol is 0 and the topmost symbol is also 0 on the stack, then we move to the next input symbol, okay, and the topmost symbol is popped from the stack. So it indicates that we do not change the state, rather we stay in the state Q1, but the topmost symbol of the stack is popped up. Same is done for the case of 1. If 1 is the input symbol and it is found that 1 is also present on the topmost symbol of the stack, so still remain in the state Q1, but the symbol is popped up. So in this way, this popping up is done, the popping up the symbol is done on seeing the symbol. So this indicates that this state will verify the WR with the W which is stored in the stack. So if we arrive, so suppose we still reach a case where we are in Q1 and we found all the symbols are popped from the stack, so that indicates that Z0 is present as the topmost symbol on the stack, and there is no more symbol to consume in the input string, that indicates that we have seen WR followed by the W followed by WR. So in this case, the transition will lead to the acceptance state Q2 without changing the stack. So this defines all the transitions of an NPDA, okay, that is required to define the PDA for palindrome language. So this is the symbols. We will see how we can define a state diagram of PDA. Alright. So imagine that if a transition for a PDA is given in this form, okay, that can be represented diagrammatically, okay, in this form, in this form, okay. So here the delta Qi Ax, if they contain the state Qj with stack having y, then that is indicated in this way: A comma x slash y. So this slash separates the symbols which is currently on the top of the stack, and the right side of the slash or the second part of the stack indicate the replacement string, what is going to be replaced on the top of the stack. If x is equal, this x and y are same, then stack remains unchanged. So here is the state diagram for the palindrome language. So we can very well see that. So this is a transition to the starting state where the stack remain unchanged, which the top of the Z0 will be on the top of the stack, indicating the starting symbol. So we can reach the Q0 by consuming any empty string, and here it indicates all the transition that is done to consume W, or that is to see that we haven't seen the end of the W. So even it doesn't matter what symbol is present on the top of the stack, whether it's a Z0 or it is 0, it is 1. On seeing a symbol 0 or 1, it is always pushed into the stack, assuming that this symbol is not the end of W. Okay. Once it has seen the end of the W, the next transition is on E, the spontaneous transition. Doesn't matter what is the stack state is. So in this transition, only state is changed from Q0 to Q1. Here the state is not changed, but the stack is updated with the symbol from the input symbol that is pushed into the stack. So here state is unchanged, only state is changed from Q0 to Q1. Now Q1 is to pop up the symbols if there is a match. So if the current symbol match with the symbol on the top of the symbol, popped up. Okay, same is applied for 1. So this is done until the Q1 arrives at the state such that it is consumed all the symbols and the Z0 is present on the top of the stack. So in this case, it will make it a transition, again spontaneous transition to reach Q2, which is an acceptance state. So this will indicate that we can reach this state only if you see the reverse of W by popping up all the symbol from the stack. So this they define the PDA, which will accept only the strings which belongs to the language L, or which is a palindrome. So this is another example for balanced parentheses. Similarly, you can see that it verifies that whether the number of parentheses, left and right parentheses, are balanced in the string. Okay, so it is very well similar to the previous diagram. So when it finds a left parenthesis, doesn't matter what in the Q0, whatever the topmost symbol is, it will always be pushed into the stack. Okay, on finding a right parenthesis, the state changes from Q0 to Q1 and start popping up the leftmost parenthesis which is present on the top of the stack. Okay, so this is done. So in Q1, once it is popped, when it is found that all the input symbols are consumed and there is no symbol present in the stack, so then it can move to acceptance state. Very similar to the previous one. So we can use a notation to represent any instance of a PDA transition. So a PDA has a triple configuration at any given instant of time. So you know that one is the state, one is the input status, and next is the status of the stack. Okay, so QW gamma can indicate any instance of a PDA. So a Q will be the current state, W is the remainder of the inputs, mean unconsumed string. What is the string? The remaining of the string which is unconsumed, and gamma indicates the current stack content. What is the from top to bottom? So gamma will indicate all combination of string which is from top to bottom. And using this triple configuration, or we also call the instantaneous description of PDA. So this is going to help us to describe the PDA. So take a PDA P. Let's say we have already defined a PDA P. Okay, then we can use a notation that is called turn style notation. Okay, to define a move from one instance to another. So assume that if we have a transition with, that is QAX, okay, a transition QAX which will contain P comma alpha, then we can also show that from the instance Q comma AW comma X beta, we can have a move to another instance of the PDA, that is P comma W comma alpha beta. So what it indicates? It says that if one of the instance we have Q, we are in the Q state of Q, and the current unconsumed string is AW, and the top of the stack is the symbol containing the symbol X followed by beta. So it says that in this move we will change from the state Q to P by consuming the input symbol A and replacing the topmost symbol X by alpha. So this is indicated by this notation. So this notation very concisely indicate this transition or indicate this move. Moreover, we can also use this symbol along with the clean closure to represent 0 or more moves, 0 or any number of moves. So we can indicate the multiple moves from one instance to another instance by using this notation. And we will be using this notation to define the theorems which describe more about the properties of PDA. So here is an example of describing the transition, defining the transition, all possible transition, okay, for the string 4 ones, the language palindrome. Okay, so each of the state, now you can see that each state of the PDA is easily described by using this triple representation. Okay, so I'll show you just 2 or 3 examples. So showing that here it is a starting state where Q0 and the unconsumed string is 4 ones, then there is no symbol other than the starting symbol on the stack. So here at this point we can have two moves, means there can be two possibility. Okay, one is that it can assume it is to the Q0 and another can be an instant spontaneous transition to Q1. Okay, so let us follow this one, that okay, it has on input symbol 1 on the, so the transition for Q0 on input symbol 1 Z0, okay, it stays in the same state, okay, by pushing this first input symbol into the stack. Okay, one transition. Second case, on looking at the second symbol 1, doesn't matter whatever the status of the stack is, it pushes the second symbol into the stack. So these two steps shows two moves, okay, from the starting state to this state. So it can show that there is a path, okay, there is a path, okay, path of moves from two moves, so that from this instance of PDA we can reach to this instance of PDA, valid moves. Okay, so there will be, so since it's NFA, we can have many branches. So one of the, if one of the branch or one of the path leads to the acceptance state, then we say that this string is accepted. So since this string is a palindrome, so one of the path will definitely lead to an acceptance state. Okay, so you can see that this path leads to the acceptance state. So this string is accepted. So it's very well said that the instantaneous description of the PDA can easily represent the transition of PDA. So let us look at these two theorems, which are very important to describe the now this transitional moves, or the nature of the transitional move. What the valid moves. So if P is a PDA and there is a multiple move, we can say that a 0 or more move from this instant to this instant, indicating that we can change from state Q to, we can reach from state Q to state P, okay, by consuming a part of X leading to Y, where Y will remain the unconsumed string, and replacing the symbol alpha from the start by beta. If there exists a move in this way, then for any string W, okay, and any symbol gamma in the tau star, okay, we also can show that there exists a move from the instance, okay, Q comma XW alpha gamma to P comma YW comma beta gamma, indicating that we can have a move, okay, step of 0 or more moves from Q state, okay, to P state, okay, by consuming the number of a part of the symbol X, okay, remaining or leaving Y, and replacing the topmost symbols alpha by beta. Similarly, if this is the case, okay, so it indicates, what this indicates is that it is irrespective what is the remaining symbol, okay, that is remain unconsumed, or what remains on the bottom of the star, okay, we can always make a move. We can always move from the state Q to P, irrespective of the remaining input or irrespective of the remaining symbols on the top of the star. So if there is a move on this case, we can always, on this case means all on X, from by consuming X, okay, part of the X, and we can, by replacing alpha by beta, so we can perform this irrespective of what are the remaining characters or remaining string or remaining symbol on the top of the stack, okay, this move can be done. So this theorem is also indicated the same. So let us see that how we can define the languages of PDA. Okay, so languages means those strings which are acceptable by PDA. So a PDA will accept those strings. So how can you define? So acceptance of PDA is defined by two ways, that is acceptance by final state and acceptance by empty state. First, let us see what is acceptance by final state. So a PDA P will then if a PDA P is defined by the 7 tuple, okay, then the language accepted by final state, which is defined, is shown by LP, is defined by all the string W such that from an instance of PDA Q0, W Z0, okay, there exists, okay, a instance, exists a transition to the instance Q, E, alpha with 0 or more moves. Okay, so saying that we can change from the state Q0 to a state Q, okay, by consuming the complete input string W and replacing the start symbol Z0 by alpha, okay, and reaching to the state Q where Q belongs to the F, or Q is, or some state belongs to the acceptance state. Then in this case W is in L, or W is a string belongs to the language defined by the PDA P. So this is by acceptance. This is very similar to the acceptance which is done by DFA or NFA. Means by making any transition, by consuming the string W, okay, by any number of moves, if we reach a state, okay, Q, by consuming all the input, irrespective of what are the symbols that are present on the top of the stack, if we reach the Q, which is an acceptance state, we accept the string. This is the definition of acceptance by final state. But since there is a stack, there is also, we have a definition by acceptance by empty stack. So let P be a PDA, and the language accepted by empty stack NP is defined by all the string W such that there is a move from the instance of Q0, W, Z0 to the instance Q, E, E with 0 or more moves. In other words, we change the state from Q0 to a state Q by consuming all the input string W and replacing the starting state Z0 by the empty string into the stack. Means the stack will, in this state, the last stack is going to be empty. So for any state Q, okay, if this condition is true, we accept the W. So NP is a set of input W that P can consume and at the same time empties the stack. See, here is the example defining the PDA which accept by final state and accept by empty stack. So the parenthesis problem. So here is by final state. So in its Q0, you can see that in Q0, irrespective of the symbol Z0 or left parenthesis or right parenthesis or okay, whatever present, if it sees, it finds a left parenthesis, always it is pushed into the stack. But when it finds a right parenthesis, okay, the left parenthesis from the stack is popped up. Okay, and when it finds the stack is empty and all the input is consumed, so there is a transition to the acceptance state. And the same thing is shown in terms of the empty stack. Okay, so here it is accepted when the stack becomes empty and all the input symbol is consumed, and this is shown by this state. Okay, these two steps remain the same. Okay, whereas this additional step is defined on the same state without showing another state as an acceptance state. So when the input symbol is empty and the topmost symbol that is present on the stack is Z0, then it is replaced by, so it is simply popped up and the stack is made empty to indicate that this is an acceptance state. Now we can construct PDA PF and from Pn. So where PDA PF indicates the PDA which accepts by final state, and PN indicates the which accepts the language by empty stack. So these are both are interrelated. So saying that if we can define a language which is accepted, or language which is accepted by a PDA by empty stack, then definitely there exists another PDA PF, okay, which accepts by final state such that it accepts the language PF. Okay, so this language can be accepted by any of this PDA. Right. So these are both are equivalent. So let us see how we can construct a PDA PF from PN. Okay. So assume that we have been given a PDA PN, okay, which is indicated by this inner circle that we can see. All right. This circle which indicates a PN, that means this PDA accept by empty stack. All right. So saying that in any state, it can accept the string at any state where it finds that all the inputs are consumed and the stack is empty. All right. So how can you convert this into the PDA with acceptance state? So that it can be done by introducing two more symbols, that is starting state and the final state, okay, a new acceptance state, and make a transition on each transition to this state, okay, and introducing a new start variable, okay, which indicates the starting state of the PF, all right, and we will pop up that symbol while making the transition from all the state to the acceptance state. Okay, so this will indicate that, okay, by reaching any state where such that we have consumed all the inputs, okay, then we can make a transition on E to reach to this final state. So let us see how we can define this construction process. So a PF is defined in this way. So if the specification of PF given PN is defined in this way. So Q is added with two new states, that is P0 and PF. P0 indicates the starting state of PF, and the capital PF, and PF indicates the acceptance state of the PF. Alright, and a new starting state is introduced into the stack symbol, topmost symbol. Stack topmost symbol is introduced in the tau. Okay, so X0 is going to become the start symbol for the stack of PF. Alright, and PF is going to become your acceptance state. So here these transitions are defined in this follow. So how many transitions we define? We will define one transition from the new starting state to the old starting state of PN. Okay, here we simply push the topmost symbol or the starting symbol of PN into the stack, and without consuming any input. And for all these transitions, we simply make transition on E by simply popping up the X0 which is present at the bottom and making the stack empty. So this is indicated by this, and all other transitions remain adjectives. Okay, so delta F P0 EX0 is going to change the state from P0 to Q0 by consuming nothing and pushing the topmost symbol, the start symbol of the stack G0 into the stack. And for all other stack Qs, for all Qs Q which is present in the set Q, and the symbol A in sigma, and for all the stack symbol in tau, the transitions delta F Q A Y will contain all the pairs that are already present in delta N Q A Y. Means all the remaining transitions are going to remain the same. So what are the transitions that are defined in this PN are going to remain the same. Only some additional transition to be defined, that is delta F QEX0 will contain PFE, indicating that these are the state. This is the state which is defined the acceptance state by empty stack. okay, for Pn. So from this we are making a move on an E string to the newly defined start acceptance state by replacing the symbol, the start symbol in the start by empty string. So here is an example for defining how we make a empty stack to a final state. Okay, so look at this diagram. So this is by empty stack. All right, we know. So we are introducing for this. We'll introduce two new states, P0, PF. All right, these all transitions will remain as it was. Only thing that on consuming the input string E, okay, we push the starting symbol G0, okay, starting symbol G0 of the stack to the stack, okay, by making a transition from P0 to Q0. Then from Q0, which are nothing but also can indicate all the state where we may consume all the string, okay, and the stack is empty. Indicating stack is empty, and indicating that here the stack is empty indicates that the x0 is present at the bottom. Okay, so in this case we simply make a E transition from Q0 to the newly acceptance state, okay, without changing the state. Okay, or we can consume, so that doesn't matter. So we have to make a move here. We have to make a move from Q0 to PF, okay, if the condition is satisfied that there is no more input and the stack is empty. Stack contains the topmost symbol, the starting symbol of the PF. So then we can make a move to PF to show that we accept this string. So similarly, the construction of Pn can be done from PF. Okay, so that is how it is possible. Now we know that PF accepts the string by final state. That means whenever by consuming the entire string, if you are present in any of the starting acceptance state, doesn't matter, the stack may be empty or not empty, or stack may be partially filled or any symbol, we accept the string. Now when to convert this PF into Pn by that means by acceptance by empty stack, from this acceptance state we can allow a E move to a state where we consume whatever the state which we will replace whatever the symbol present in the stack by empty string. So that means by reaching P we will have no string to consume, and at the same time whatever the symbols that were present in the stack at this acceptance state all are going to be popped up by reaching P. So P will have a state, a state which will indicate that there is no string present and no string to consume, and the stack is empty. Alright, so this is the transition to be defined, and the same way we have to define a new starting state to add the new stack symbol into the stack to indicate that this is required, because this will denote that we have reached the end of this and acceptance states. Okay, so let us define this one. Okay, so let us design the specification Pn, which is given by Q with the new two states. Okay, P0 and P. P indicate the state of empty stack. X0 is a new starting symbol for the Pn. Okay, and where we define the transition in this value, the delta n of P0 E x0 will be Q0 G0 x0, which is similar to while we are converting from PF to Pn, we are pushing the starting state of PF into the stack. And for all other transitions remain the same. One thing we have to add here is that from all acceptance state here, where for all Q belongs to F, we have to add a transition delta n Q E Y, okay, which will contain the state P, which will make a move to P by consuming or by replacing all the symbols that are present on the top of the stack by E. And also we have to add one more thing, that being in the state P, okay, we may reach, because there is a E move, we may reach by having maybe any symbol to the stack. So since there are E moves, we may reach to this P state by having still some symbol on the stack. So we can define additional transition, saying that on delta n, being in state P, okay, we will make a transition to the state P by staying in the same P, but we will replace all the symbol from Y, which is in the stack, by empty string. So this is indicating that if we reach P by having some stack symbol, then we can make this move to clean or to empty the stack. So this will indicate that stack will become empty and the string is accepted. Next, as we say that for every context-free grammar we can define a PDA. Alright. So we'll show the equivalence of context-free grammar and PDA by showing the conversion that given a context-free grammar we can construct a PDA, and the same way given a PDA we can construct a CFG. So these two conversions will indicate that both are equivalent to each other. A CFG is equivalent to its equivalent PDA. So let us start with the conversion from a context-free grammar to the PDA. So given a context-free grammar, let's say G, okay, we have to construct a PDA P that accepts the language defined by the grammar by empty stack. Okay, so we indicate this by empty stack as follows. So we define a P such that a Q stat Q is defined, okay, and the stack symbols are going to be the union of all variables and or all non-terminals and terminals of the grammar, and S going to be the starting state of the stack and Q going to be the starting state of the states. Alright. So we define the transition in this way using the production of the grammar. So for each variable A present in the grammar, we define a transition in this way. Delta Q comma EA will contain Q comma beta such that if there is a production with A produced, beta is in the G. Alright. So for every variable A, using its production A produced beta, we can say that we can make a move without consuming any input simply by replace. If A is found on the top of the stack, we can replace the A by its body in the top of the stack. Second step says that for each terminal A, if we find that the current input symbol is A and the same terminal symbol is present on the top of the stack, then we simply pop up the symbol from the stack, okay, and proceed to the next symbol. So this is indicated by the next the resulting state Q comma E. Okay. So in this way, given all the productions, okay, we can define a PDA. So here is the example. So given this grammar, we can construct a PDA like this. Alright. So for all the states, okay, for all the states that has been given, okay, we can define S and E for all variables S and A. Based on their productions, we can define the transition Q comma E comma S by replacing by the state with its body. So Q comma AS or Q comma E, where AS and E are the body of the production for the symbol S. Similarly, you can see that 0 A1, A1, 0 1 are the body of the production for A. So we can define a transition by whenever on A is present at the top of the star by replacing A by its body of production. So these are the two transitions, and for all terminals we define these two transitions. That is, if you see this 0 on the top on the input symbol and on the top of the star, we can simply pop up. Similarly, for 1 also we will do the pop up. So this is how we define the PDA from the context-free grammar, and it is also can be proved that this PDA is equivalent to this PDA except the same language defined by the grammar G. Next is, given a PDA, convert into its equivalent context-free grammar. Okay, it is a bit tricky, so you have to understand the few aspects here. That is, S is a special, S is considered as a special symbol in from the PDA. Okay, so let's say we are going to construct the grammar G where V, sigma, R, S to be defined. Okay, so S is a starting symbol. Consider S as a starting symbol. Then we'll define the production for S. Okay, so all symbols will be in the form of P, X, Q. So it is indicating that the transition of from P to Q. So we define a variable in this form to indicate that it indicates the transition from the state P to the Q by replacing the variable X. So we are going to remove the X. So while making a transition from P to Q, we are going to remove X. So that is defined by a variable in the grammar. Okay, so that's why we combine them to indicate a single variable. Okay, so the production that is to be introduced in G, okay, using the PDA information are as follows. So for all the states P present in the in the PDA, the G will have a production from the starting state S, okay, to the symbol that is Q0 Z0P. So indicating that it indicates the transition from Q0 to all the state P, okay, by removing the symbol P. So we can reach to any state P by removing the starting symbol of the stack or emptying the stack Z0. Second, if we have a transition, okay, so that from the state Q we can reach the state R by consuming the input symbol A, okay, and replacing the start symbol X by y1, y2, y2, yk, by a number of variables y1, y2, yk. Okay, then for a list of states R1, R2, Rk in present in the PDA, we define the production in this manner in the G. So that is, to reach from the state Q to Rk, okay, by removing the symbol X, that, okay, so this variable can produce the number of variables. Okay, so first by reading A, so we can achieve this, and I'm saying that we can achieve the transition from Q to Rk by removing X symbol, okay, can be achieved by first reading the terminal symbol A, then by making the transition from R to R1 by removing this Y1 by considering any input symbol, then by removing Y2, okay, by transition from R1 to R2, okay, similarly, so we can by having transition from state Rk minus 1 to K by removing Yk. So this is the production. We indicate the transition in the PDA. So here is the example. So the same way it is defined. So we will discuss this example further. Next is the deterministic PDA. So till now whatever we have discussed is all about non-deterministic PDA where it involves E transition. So the deterministic PDA ensures that it is deterministic, okay, and it holds the following condition, which is almost similar to the conditions that we impose on a DFA. So first is that any transition, let's say del QAX, has at most one member. So indicating that we cannot have multiple moves. We will have only exactly one move on one transition, move to exactly one instant. Secondly, if delta QAX is non-empty for some symbol A, then it says that on input symbol E, we may not go to any state. So it says that delta transition on E is empty, saying that we cannot have transition on E. There is no transition on deterministic PDA. So how deterministic PDA is related to this context-free language? So deterministic PDA can define, okay, can accept the languages which are regular languages, and also it is the languages which are between regular languages and context-free languages. Now remember, if a language is accepted by deterministic PDA, then the language is an unambiguous context-free language, okay, or unambiguous context-free grammar. If the language is ambiguous, then it can be designed, or you can design a PDA which is non-deterministic, but we cannot design a deterministic PDA if the language is ambiguous. The language for context-free grammar is ambiguous. So that is the nature. So these are very much, so deterministic PDA are very much helpful in designing the parser, deterministic parser. Okay. So here is an example of deterministic PDA for the language W, C, WR, where C is a single symbol, okay, a single symbol which lies between the W and its reverse string W. So here it is for taking this W, by indicating all zeros and ones, it will stay in the Q0, while on seeing the symbol C, it make a transition to Q1. Okay, so and then in Q1 it try to verify the WR. Once it is verified, the stack is empty and all the inputs are consumed, then it make a moves to the Q2. So this is all about PDA, NPDA and deterministic PDA. That's all for this session.